And we're back. Okay, next up we have our caramel sitting here. It's cooled a little bit by now. And it's time to add a little bit of salt, because salt and sugar always taste good together. So we're just going to sprinkle this right on the top.
This is salt toffee.
Oh yes, delicious. Here we go. And Sarah, you want to grab some nuts?
Ooh, nuts. Okay, Sarah.
I think nuts are pretty great, so I'm going to start adding some of these. Now I'm going to...
Nuts are pretty not great.
Not great nuts. Sarah, you're crazy. You know
I'm
what?
nuts.
You are nuts, but I am nuts for nuts. I love pecans on my toffee. Okay, now where we left in the kitchen, I am currently adding nuts to the toffee. This is my favorite part of the toffee, so I'm adding nuts at a pretty quick rate. I'm adding 2.5 nuts every second. And these are all crumpled up nuts, so we can add less than a whole nut at a time. Now, I want to find out how many nuts I add in between time 7 seconds and time 13 seconds. And at the rate of 2.5 nuts per second. And to do this, I'm going to use an integral. So that means we're going to set the integral using our nice integral sign here with the bounds 7 and 13 and our rate, and then we have this dx here to show that we're integrating with respect to x. Now the first step of an integral, evaluating it, is to find the antiderivative of the rate. And with our rate being 2.5, we know that the antiderivative, or the thing that when you take the derivative of it gets this, is 2.5x. And when you take the derivative of this, 2.5x, we know that it's 2.5, so we've got the right antiderivative. Now to show the antiderivative is being evaluated between 7 and 13, we put this nice long vertical line, and 13 on the top and 7 on the bottom, to show those are our bounds. Now, when we evaluate this, we know that n, or the number of nuts, is equal to 2.5 times the greater bound minus 2.5 times the lower bound. So that's going to be 2.5 times 13 minus 2.5 times 7. And n equals 32.5 minus 17.5. And that gives us an n of 15 nuts added between time 7 and time 13. Okay, I'm just going to add a few more. Sarah, stop taking these off, will you?
I just
the best
know how long
part.
it'll take for me to get them all off. We could figure that out with calculus.
I bet we could.
To the whiteboard.
Yup. Okay, where we left off, I was still adding nuts at 2.5 nuts per second, and Sarah just decided that she doesn't want nuts. I mean the little Sarah, of course. And she is removing them at a faster rate of 3.3 nuts per second, starting at time 20. And we want to figure out how long until there are no nuts left at all on the toffee. Now to do this, we have to first figure out how many nuts are on the toffee in total at time 20 before Sarah starts removing them. And to do that, we follow the same procedure as the last problem, in which we're going to integrate from 0 to 20, our rate, which is 2.5 dx. And the dx shows that we are integrating with respect to x. Now, the first step is finding the antiderivative of our rate, which is going to be 2.5x, because if you take the derivative of 2.5x, we get our rate of 2.5. And we are going to integrate this from 0 to 20 times 0 times 20. So we're going to go ahead and have our bounds, and we are going to plug those in. So it's 2.5 times 20 minus 2.5 times 0. And this term, because we're multiplying by 0, is just 0. So we're going to cross that out because it doesn't really matter. But this term shows us that the number of nuts at time 20 is 50. So at time 20, there are 50 nuts. Okay, so now we know how many nuts there are when she starts adding them, or sorry, taking them off. And we need to figure out how long it'll take until there are none left. So we're going to set up another integral, starting at time 20, but we're going to take this integral all the way to time t, because we don't know how long it's going to be yet. And our rate this time is going to be a combination of our two rates. So my rate is positive because I'm adding nuts, so it's going to be a positive 2.5. But Sarah's rate is going to be negative because she's removing nuts, so that's going to be a negative 3.3. And again, we're going to use dx. Now, just like last time, we are going to take the antiderivative of this term, and just so you know, this term is equal to negative 0.8. So our antiderivative is negative 0.8x, and we're taking this from 20 to t. And because we know we have to have 50 nuts removed, we are going to make this equal to negative 50 in both cases. Now we're going to plug in our two bounds into this problem, just like we did over here, and that's going to give us negative 0.8t minus negative 0.8 times 20. And that is all still going to equal negative 50. Now, negative 0.8t minus, and this comes out to 16, so minus a negative 16, which is equal to positive 16, of course, is equal to negative 50. Once we subtract this over, it's going to be negative 0.8t is equal to a negative 66 nuts. And we have to divide both sides by negative 0.8. And that's going to give us a t equal to 82.5 seconds. Now, because this is kind of a large number of seconds, it's easier to convert into minutes. So we're going to divide this by 60 to get minutes. And that is equal to 1.375 minutes. So to recap, at time 20, Sarah started taking us off, and I'm still adding, and it takes a total of 1.375 minutes for there to be no nuts left on the toffee. And next we're going to add some chocolates. I love chocolate myself. We got some.
Well, who doesn't love chocolate, Sarah?
How much is this, Sarah? 6 ounces, was it?
6 ounces of chocolate chips, Sarah.
Yes, and do you want to help add these? We're going to sprinkle these over while the toffee is still fairly warm.
Hopefully it'll melt them.
Yep. And as they melt, we're going to try to spread them around a little more. Might have been a little too late with these, but that's okay.
It did take a lot of time to add those nuts because of all that
Somebody
arguing.
kept taking them off.
I'm telling you, Sarah, nuts is a bad idea.
Nuts are good. They're so good. Lots of protein for us vegetarians. Here you go. You can do the last little bit.
Why, thank you, Sarah.
Oh, one more. There you go. And let me grab a spatula so we can spread these out nice and evenly as they melt. Push them in a little bit if they're melting. Is it still warm? It cooled really fast.
Yeah.
Okay, we're just about finished up. We're gonna let this melt a little while longer, and we'll see you in a few minutes. Here we go.
Oh, look at that nice
Our chocolate's starting to melt.
texture.
Yeah, we're gonna spread it out over the whole toffee. Because everyone wants a little bit of chocolate in their piece, don't you think?
Well, I certainly hope so.
You know who I bet would like some chocolate?
Who, Sarah?
I got Mr. Wilson, our best calc teacher in the whole wide world.
The best teacher who ever existed.
Oh, he is just the greatest. And I'm sure he would love some toffee, especially because we use so much calculus, figuring out all these related rates and all these
Well, that is
different
the
problems.
point of calculus, isn't it? To figure out how to cook things.
Oh yeah, cooking is everything. Okay, would you call that fairly even?
I would say that's decently even.
Do you want to lick a
Sarah.
spoon?
Why, of course, Sarah. It is chocolate.
Yes. Now we have one last problem to figure out. So as you can see, our beautiful toffee right here is a very round shape, but we have a square Tupperware, and we need to figure out what is the biggest size circle we can make this toffee to fit it in our standard square Tupperware. So why don't you guys meet us in the whiteboard, and we'll see how well we can fit everything together.
When you last saw us in the kitchen, we were storing our toffee. Now, we have a Tupperware that's a square Tupperware that's roughly 40 centimeters by 40 centimeters. We have to put a circular toffee in it. So we need to find the area of the largest circular toffee that fits in this square Tupperware. Now, in order to do that, we have to model the area of the toffee. Since the toffee is a circle, we can model it with the function pi r squared equals your area. Now we want to find the maximum area, so in order to find the maximum, we want to take the derivative of our existing function. That can be seen as, because of the power rule, 2 pi r equals dA over dr. Now, we find where the area equals 0 in order to find maximums and minimums on that graph. 2 pi r only equals 0 when r equals 0. But we have to remember to check our endpoints. Now we know that our left-hand endpoint is 0 because it has to be a real distance, so it has to be a positive number. But our right-hand endpoint has to equal 20 because that's half of the longest possible diameter that fits in a 40 centimeter Tupperware. So now we have to check r equals 0 and r equals 20. We can check if they're a maximum or a minimum by charting them. Because r equals 0 is a local maximum minimum as opposed to just an endpoint, we can chart it from both sides. The way we do this is we plug in a number directly to the left of 0, like say -1, to our derivative equation to find the slope. And since -1 is negative in this case, because it's -2 pi, we know that the slope here is negative. Now we can plug in a slope directly to the right, and you know that it's positive because the positive 1 is 2 pi. So now you know that our slope goes from negative to 0 to positive, making 0 a minimum. Now when we check 20, it's only an endpoint, so you can only chart it from one side. Since it's a right-hand endpoint, you can only chart it from the right. Now you pick a point directly smaller than 20, like 19, and you plug it in and you still get a positive number. So you know that our slope is positive as the number approaches 20, so 20 has to be a maximum. Therefore, our maximum on the interval from 0 to 20 is 20. Now we can plug 20 back into our original equation to find the area at 20, and we find that it's pi times 20 squared, or 400 pi. So we know that the maximum area of the toffee that can be stored in this container is 400 pi.
Did you enjoy that spoon?
Yeah.
I'm gonna shake it a sec. Okay. And we're back. I hope you guys learned a lot through our calc demos today. As you can see, we made this beautiful English toffee. It's sugar and lots of butter, a little bit of water.
Lots of nuts.
Nuts are so good, and plenty of chocolate all over the top. And all we have left to do now is break it up into little pieces, put it in Tupperware.
Feed it to our calculus class.
Oh yes, our calculus class is gonna love this. Well, signing off, I'm Sarah.
And I'm Sarah.
And this is Cooking with Sarah. Okay, we good?
We good.
Let's smash this.